All right, thank you so much for the, can you hear me? Yeah, thank you so much for the introduction. I'm Diamond Wang from USA Riverside, and this is a joint work for Virginia Tech and the US Army Research Lab. With introduction out of the way, let's go steal some keystrokes. Now, graphics is of course very essential to our everyday computer life, and the graphic rendering is a complex process. To just render a single text on the screen, we have to translate that from ASCII code and into some bitmap representation, and then put it on the screen. So this process usually involves a ton of libraries, and the inner workings is very complex. Now, let's take a look at this example, which is a code from Scale graphic library. So you can see in the first function, it's scanning row by row, and in each row, it calls a second function, which scans left to right, pixel by pixel. And if there's nothing to do for one specific pixel, you just skip. So one problem for this is that it is not constant time. For text with more pixels, it will take longer to render than the text with lower number of pixels. So this could create a potential side channel, right? So if the attacker can know when the text rendering starts and when text rendering finish, the attacker can measure the rendering time and thus infer what key is being rendered on screen. And this is important because for many applications, it will render your input on the screen, no matter whether you are just a simple input box or you are using something like on-screen keyboard. So let's take a look at this Onboard on-screen keyboard that comes with Ubuntu. You can use it when you have a touch screen, or you might want to use it for more security according to this article. And when you press a key, like many other keyboards, it will render a highlight of the key you just pressed along with the text inside. So that creates an attack opportunity. Now, here's the measured execution rendering time of different keys. As you can see clearly, some keys take longer to render than others. So that's it, right? Thanks for coming. Except it's not that simple. So to make the attack actually work, there are some technical challenges we must address. So first of all, how do attackers perform measurement if it's unprivileged? In this case, the attacker does not have direct access to the victim's execution state. So the attacker has to figure something out. The second challenge, as we mentioned before, is that graphic rendering is a very complex process. It involves millions of lines of code and multiple libraries. What makes it worse is that the rendering process often varies from application to application. Manually going through all of these is obviously a tedious job and is not very efficient. So we are wondering if there are any automated approach to discover side channels. And the final challenge is that we are a timing side channel after all, so we have to deal with noise. The noise can come from the victim side and the attacker side. From the victim side, because of features like CPU cache, TLB, branch prediction. Even when they're in the same key, the timing will be different. And from the attacker side, since attackers don't have direct access to victim's execution state, whatever methodology it comes up with will potentially have measurement error and measurement noise. So given a potentially noisy measurement, can the attacker still infer what is being rendered on screen? So here's all the challenges. Let's go ahead and solve them. Before I do that, let's make the threat model clear, okay? So the attacker's goal is to eavesdrop sensitive text input that will be rendered on screen. That could be a PIN, a password, or username. And as for attacker's capabilities, we make two assumptions. The first one is we assume that the attacker has the same model and version of the hardware and the graphic libraries. So in this way, the attacker can simulate users' input offline and study the behavior of victim application and graphic libraries. The second assumption we make is that the attacker will be able to install an unprivileged malware on the victim's device. So when the victim is about to enter some sensitive text, the attacker can launch a process around it. Okay, challenge 1, how to perform measurement. So we are talking about unprivileged attacker. So not allowed being shared between attacker and the victim, except for graphic libraries, which is often provided by the operating system to be used for all processes. When we say share, what it essentially means is that for the same function in the same library, it will always be mapped to the same physical address. Another thing being shared is the CPU cache, of course, which is the CPU last level cache is often physically indexed. So which combined with the previous condition, it means same function, same library will always go to the same cache set. Now, if you are familiar with CPU side channels, these immediately spells out flush and reload. For those of you who are not familiar with it, here's how it works. So attacker starts by flushing the CPU cache and then access one of the function. Let's say render start. Now, because it just flushed it out of the cache, the access will be slower. However, if after flush, the victim somehow access render start as well, then the attacker's reload will be much faster because the victim just brought it into the cache. As a result, the attacker can thus take a timestamp saying that, OK, here's you start rendering, and do the similar thing for the render end, and then compute the time difference to infer the render time. Now, in this attack, attacker has to flush, and reload over and over. So it has a limited resolution. So in our onboard case, for example, we are able to do 600 nanoseconds per round, which is not ideal, but comparing to the actual rendering time, 350 microseconds, we're pretty good. OK, so second challenge, how to perform side channel discovery in an automated fashion. So I do this by instrumenting the graphic libraries and collect victim program trace. The program trace is basically a time series saying at what time, what address in the graphic libraries will be executed by the victim. So we do this for all the possible inputs and collect a lot of traces. From these traces, we can get a lot of potential address pairs that the attacker can monitor. But not all of them are good. For example, let's take a look at the first one, A0, A1. This looks pretty nice, right? We're rendering A, the time is shorter. Rendering B, the time is longer. But we have the problem of flush and reload resolution. The time is too short for the flush and reload to have an accurate timing measurement. So this does not work. What about this one? The problem for this one is for the same input, there's a huge variation. So even after attacker have a timing measurement, it cannot really infer what's being rendered on screen. And this one as well, A4 and A5, because this time we don't have a lot of variations, but the timing is basically the same across all the different input. What makes a good side channel would look something like this. For example, when rendering A, the timing is consistently shorter than rendering B. To put it formally, the good side channel should be long enough for flush and reload, and should be scaled across the same input and has high information gain across different inputs. And here we also take into consideration about the cache properties that these address pairs have to satisfy. For example, we want the addresses does not cache index to the same cache set, and they don't prefetch each other. So this creates some criteria we can use to filter out address pairs that are not suitable for the attack. In our onboard case, for example, in one library, we found 6 million pairs, but after this filtering, we are left with around 1,000. Now, so far, everything we did is from an instrumented victim app. What we haven't considered so far is the system noise and the instrumentation overhead. So to get this out of the way, we perform a sanity check by just run the attack offline. So this will filter out address pairs that are affected by system noise and the instrumentation. So with this level, after this filtering, we are left with less than 100 pairs. The final piece of the puzzle is how to perform Keypress prediction given a potentially still noisy timing measurement. So we do this by constructing a machine learning model based on using the data we collected offline. So we choose random forest in this case. And during the attack, when the attacker have a timing measurement, the classifier will be able to tell what key it is with certain confidence. For example, in here, when as being rendered, it may say as has 0.7 confidence, etc. So there goes all of our challenges. Let's go back to the attack and see how it works. So first of all, the onboard attack that you see at the very beginning. So here are the top 5 side channels we discovered. We actually instrument a lot of graphic libraries, but it turns out the Cairo is the one giving us good results. And here's the Keypress prediction accuracy. So for simplicity, we only consider letters and lowercase character. So there are 36 classes. If you just do a random brute force, you will need around 32 guesses to reach 90% accuracy. But you can see in this graph, in our case, we only need around 8 guesses for most of the keys. Although to be fair, some keys are much harder to predict than others. Now, password is not often changed, so it's safe to assume attacker can potentially capture multiple login attempts to improve its accuracy. So with 10 logins, we can see a lot of characters can already be predicted with 90% accuracy in the first try. And with 20 login attempts captured, even better. Now, eventually, you want to crack password. Now, this is just individual characters. So we tested this by finding an online database of top 10,000 most common passwords. And we showed that with our attack, because in this case, if you do random brute force guess, the search space is even larger. But with our attack, since we ranked everything with confidence, we are able to do 1,000 to 1,000,000 times faster than random guess. Can we do even better? So when we do password cracking, one useful tool is a password dictionary. So if you have no other information, you can just go through all the passwords in the dictionary and try it one by one until it works. But with our attack, we can rank all the password in dictionary with confidence and improve the password cracking capacity. For example, here with just one login, we can crack half of the passwords in the first try. And with 10 logins, almost every password can be cracked within the first try. This is obviously very useful because many applications will lock you out if you try a password too many times. OK, that's one attack. Let's try something on Android. So we have this Capital One banking app, which you ask for username and password upon startup, like many other apps. Normally, password is not rendered on screen. But in the case of Android, for convenience of users with sick finger like me, Android will graciously input whatever you enter for 1 second, thus creating opportunity for the attacker, right? Now, we tried this on the ARM architecture, so Flush+Reload needs to go through some modifications, but has a 20 times lower resolution than the Onboard, which we do on Intel. But we still are able to find many side channels. And upon a closer examination, these side channels is actually some pre-rendering operation that's triggered only once for each individual character, which should be bad. But in our case, since the username and password input happens at the very beginning, not a lot is being pre-rendered, so we're good. Now, because of the lowered resolution, our attack is not as accurate with just one single login attempt capture. But with 10 login attempt capture, we can still predict most of the keys within 8 guesses, 90% accuracy. And with password cracking, we are doing 1,000 to 10,000 times faster than random guess. Finally, with dictionary, 30% to 60% of the password can be cracked in the first try. Depends on how many login attempts the attacker can capture. We also attack some other Android apps, which you can find in the paper. Based on our experience of the attack, we conclude that the measurement challenge is really the bottleneck of our attack. So the attacker's capacity is heavily influenced by just how fast you can do flush and reload. And also in this presentation, I'm just talking about the very basic ideas of attack. So there are a lot of extensions we can further apply. For example, our attack automatically get inter-keystroke timing, which is proven to be very useful. And we can also combine our attack with other side channels like acoustics, accelerometer, etc. And finally, our automated approach to discover side channels could be applied to other libraries. To defend against our attack, so one way is to prevent flush and reload from happening. We can do it by changing the cache architecture or disable high-resolution timers. Another more solid way is just to make everything constant time, but with some slight performance overhead. Okay, to conclude, first we figure out a way to measure execution time from one process to another. And we find an automated approach to expose side channels in graphic libraries, even without much understanding of the internal works. And finally, we evaluate our attack on real-world applications and demonstrate that our attack is practical. We would like to thank again of our collaborators from the CRA program, and that concludes my talk. Thank you very much.
So I will start with one question. So you mentioned some of the mitigation in the end of your talk. Have you considered the mitigation like randomize the layout of the keyboard, the display of the keyboard?
Yeah, randomizing the layout of the keyboard does not really work because we are talking about the text rendering, the rendering of the text, the time it takes to render a text. So if you have the same font all the time, it's still not going to work. But one thing you can do is randomize the size of the key. That will give us a lot of headache.